We are back in the Space Vehicle Mock-Up Facility, Building 9 here at Johnson Space Center, where for the past couple of weeks, the RATS Research and Technology Studies group has been simulating a mission to an asteroid. We talked last week with a couple of the specific parts of the test, and today we're back to talk with Andrew Abercromby, who is the principal investigator for the test. Thanks so much for talking with us, Andrew.
Pleasure.
Okay, so RATS, Research and Technology Studies, one of several analogs that we do. Tell us why we do analogs and what we're getting out of this one.
Okay, so yeah, this is part of what we call an integrated analogs program, where we combine testing at facilities such as Johnson Space Center, Neutral Buoyancy Lab, as well as field analogs such as Desert RATS, which is when we're out in the Arizona desert, NEMO, which is our underwater analog off of Key Largo. What we're trying to do using these analog tests is we know that the technologies that we have affect the way that we operate when we're in space. We know that the way we want to operate affects the technologies that we need and what we need them to be able to do for us. And so by doing tests like this, where we do what we call integrated mission simulations, where we try and pull different technologies together, technologies that are usually at the prototype stage, such as the space exploration vehicle you see behind us, have them all work together in kind of from start to finish through at least one phase of a mission, and then see how those different technologies interact with each other, which things work well together, which things maybe don't work well together, which we need, which maybe we don't need. And by doing that early in the design process, it's relatively quick and relatively affordable to make changes, as well as to just decide, hey, maybe we don't need this technology after all, and instead we need something that we hadn't previously thought about. And so it's a way that ultimately we can spend a little money up front and have potentially significant cost and time savings further on in the development process.
Right, because you know early on kind of what you want it to look like. You don't get into space and say, I wish I had a window here, right?
That's right, yeah. The windows actually are a big part of the evaluations we've been doing with the space exploration vehicle. We've gone through, this is our Generation 2A vehicle. We had two Generation 1 vehicles before this, and actually the windows on the vehicle behind us here were generated using, we did evaluations where we had a simulation environment, a large dome onto which we could project simulations of the moon, of asteroids, even of Mars, and then do simulated tasks, driving, flying, even landing, and see how the different configurations of windows actually, how well they lend themselves to the different tasks. And what we're trying to do with the space exploration vehicle is have a configuration that you won't have the exact same vehicle be able to work on an asteroid and Mars, and the moon, but by having a vehicle that has all of these potential destinations in mind, then we can make relatively small changes to a core concept, a core module, to enable exploration in these different environments.
Mm-hmm. Well, and probably what you're seeing in the background here, you can't tell much about it because the windows that we're talking about are covered in a video screen, so that we have simulations of an asteroid that the crew inside are seeing as they fly around and do spacewalks and all sorts of things.
That's right. Yeah, the screens that are surrounding the windows right now, they actually displayed on those. They have a very high fidelity simulation of Itokawa, which is a real asteroid. And actually, we used imagery and data from the Japanese space agency, JAXA, to help create that simulation. We have a really fantastic simulation team here at Johnson Space Center who created this virtual environment. The pilots inside this SEV behind us here, they can fly around this asteroid, they can interact with it, they can land on it, and then they can also see out of their windows the spacewalking astronauts who are flying jetpacks that are actually controlled from upstairs in Building 9 here in the virtual reality lab. And so really what we're trying to do, a big part of the test this year, is figuring out what's the most efficient, the safest, the most productive ways to combine these different capabilities at an asteroid. A space exploration vehicle, we have an arm that can reach out the front and actually support an astronaut on the end of it, so providing them stability to do geological sampling tasks.
Kind of like the Canadarm2 on Space Station?
A shorter version of that, if you like, yeah. Or do we have astronauts on jetpacks be delivered to the right area by the space exploration vehicle and then depart from that, which is what they're doing today, actually. They fly close in the SEV, and then once they're in the proximity, they go to their jetpack mode, go down, grab a rock, and then return to the SEV. So we're really trying to understand what are the most efficient, productive modes, how it affects crew workload. Are there potential hazards of operating one way versus another? And then also looking at the amount of propellant that we would need based on these different options. And from that data, we then figure out, okay, what does that mean for our vehicle design and for the technologies that we require? Okay.
And I know, some of these questions you've been looking at over the course of several tests. Do you feel like you're learning stuff and moving toward a better product?
Yeah. So with respect to asteroids in particular, it's been a couple of years now that we've been looking at those. I personally didn't know a great deal about asteroids when we started looking at this a couple of years back. Now we actually feel that we have a pretty good handle on at least the big pieces that we would need to explore safely and productively an asteroid. And with tests like this, we are starting to figure out, okay, with those big pieces, what are the smaller pieces that we require? Things like software, control systems, guidance modes, how big do the tanks need to be in terms of propellant, things like that. And so we're getting closer to a well-defined package of how we would explore an asteroid even when the time comes.
Would you say that you found out anything that you weren't expecting throughout these tests?
There have been, we're still at the stage now. We're testing at the moment. We're still collecting data. So it's a little early to draw any to make any bold statements about what we've learned in this test. There was a kind of one day of testing where we focused specifically on, for example, the effect of the spin rate of an asteroid, and then basically how large of an asteroid that we're exploring on, and the effect that has on the amount of propellant that we need, the workload of the pilots in terms of trying to just position a vehicle over a specific point on an asteroid. And we actually, as we hypothesized, we found that it became a harder task for our pilots as they were trying to station keep over the larger, faster spinning asteroids. But not only that, we were able to quantify, we were able to measure the amount of propellant that we would need to station keep for a period of time as a function of asteroid size and spin rate. So that's the kind of data that really allows us to have more confidence when we're trying to size the systems for this vehicle, and have confidence that when we go to an asteroid one day, we're going to be able to operate for the full mission duration and have sized our systems appropriately. Okay,
very interesting. And I know just with the space exploration vehicle itself, when we first started talking about rovers again, it was just a chassis, very cool chassis, but one that you drove in a spacesuit standing up, and now we have a cabin that people live in for days and even weeks at a time, and learning more and more about the best way to do that once it is time to go back to outside of low Earth orbit again.
That's right. Yeah, and those developments, the evolving shape of the space exploration vehicle and the capabilities are a very good example of how we're using this kind of testing to kind of incrementally, get smarter about these different destinations and have confidence that we're going to be devoting our time and funds to the right technologies.